Hi, everyone. Thank you for inviting me to this workshop. I'm Anton Petrov, Senior Research Scientist at Integrative Center for the Origins of Life. I study the ancestral biology and especially early origins of life and evolution. My focus is in my studies, it's the origins of translation machinery, which is a key component of all modern biology. So we use some, we have started to use some machine learning um, in our research, and I am attending this workshop because I would like to contribute, and I'm eager to learn new approaches that are available to us. Um, and I would like to thank Floyd for a great introductory talk because a lot of concepts and methods that he already introduced, I will be using in my talk and try to conceptualize them a little bit further. And I also, from a recent discussion, especially the recent questions that Natalie brought into just recently, a few minutes ago, I hope that some of that can be resolved in my talk. So basically, first of all, since Floyd only introduced the essential methods in the machine learnings, let me first try to introduce the key concept of this workshop, foundational model. So basically, it is a novel approach in the machine learning, or it's a machine learning or deep learning model, which is trained on a large data set so that it can be applied across a wide range of use cases. And that basically represents a paradigm shift in machine learning and requires a careful consideration of pipeline design. Machine learning pipeline is a systematic approach comprising of several key components that facilitate the development of predictive models. Machine learning pipelines are composed of sequence of linked components or steps that define the machine learning workflow to solve specific problems. Let me basically introduce the overall schema for the machine learning pipelines here, and then the rest of my talk will be covering more specific components of this schema. So the pipeline begins with the data collection, data processing, pre-processing, and then training. Then training is training of and the model selection and the training steps are essential key components for developing of pipelines for foundational models. And once initial training is achieved, then the models will be validated. So there is a model validation steps. And then basically the entire process doesn't stop here. It is an iterative process. So basically that the new updates will be coming, and then during a prediction steps, the results will be the results will be also delivered. Predictions will be added to the data, and then the cycle continues on. So this is the net overview of the pipeline. So I'll start with data collection step. What is important is, of course, we are dealing with the foundation models, and we try to collect all different heterogeneous data that includes curated database and academic repositories, user-generated content, proprietary data, API integrations and partnership, and web-scale data collections, etc. So one of the key one of the key component at this stage is the data quality, and there are a number of approaches that need to be aware of to achieve, because this is a critical step. So it's a source integration, handling missing or incomplete data, content diversity, consistency checks across the data sets, and version control. Um, and specifically, if we are focusing on uh, data related to NASA, so there are science data, which are Earth data, satellite imageries, climate and weather data sets, land use, ocean and atmospheric measurements, and then space science data, which are also available. So there are once the initial data are collected, so there are several approaches that can be utilized in order to pre-process the initial data. Those involve data ingestions, collecting data by using various frameworks, exploration and validation, which includes data profiling to obtain information about content, data wrangling, data labeling, and data splitting. Um, so, once this initial data processing has been performed, then there are several advanced techniques that can be used in order to enhance the data processing. So this includes data transformation techniques and creating new features. Some of those methods that Floyd has mentioned during his talk, like principal component analysis and key distributed neighborhood embedding. So once we have the collection of processed data, the next critical step is model design. And the model design itself contains several critical steps: model training, model evaluation, model testing, and model packaging. There are a number of architecture considerations that need to be accounted, and I hope that some of that will be brought in a more detailed fashion during the discussion. So I will just list here the most general criteria for architecture consideration, which is basically scale requirement, task-specific requirements, and resource constraints. There are several architecture types that have been used by foundational models over past number of years. The original set of models were encoder-only model, and encoder role is pivotal in understanding and encoding input sequences. It takes raw data, tokenizes into discrete elements, and transforms these elements into embeddings, which are numerical representations that encode semantic information. And these embeddings then processed to a set of identical layers. The encoder-only models have been abandoned in the past few years, and so the modern pipelines consists of either encoder-decoder models or decoder-only models. And decoder plays a pivotal role in generating sequences based on contextual information acquired by the encoder. In tasks like a language translation, the decoder takes encoded representations and generates target sequence. Decoder-only models represent distinct breed of transformers that excel in generating coherent sequences based on contextual information. So basically, the most recent advanced models used this type decoder only type. And that's basically summarizes this, the types and the architectures. So it's either decoder model only models or encoder decoder models. So they have advantages, they have limitations. So the next and the critical step is model training. I guess Floyd has mentioned some of them, some of those steps already. So it includes self-supervised learning and pre-training, which is the initial phase, where basically the initial tokenization happens, and then the model is required to predict the next step. Then there is a second stage, which includes supervised fine-tuning, where based on existing tokenizations, the data um, uh, expect to fine-tune to tailor responses, and basically it involves domain-specific data formatting and uh, for better interactions and better tasks. And then finally, on top of it, it's the most advanced type, which includes reinforcement learning from human feedback. And that's basically an award-based approach where it refines model by incorporating human feedback and training and provides the rewards for best responses. So then the next, once the model has been pre-trained, the next stages includes model evaluation, and the core objectives for this step is to assess model performance across multiple dimensions, to validate generalization capabilities, to identify potential biases and limitations, and to ensure robustness and readability. And then once the model has been evaluated, the model will need to be tested. So the original data set is divided into two halves, so that there are some data for training set, and then the second part of data is being used for testing. There are several strategies that have been applied, including comprehensive testing, diagnostic testing, and bias and fairness testing. And then finally, there is a deployment step, which includes the deployment of actual model. And at this point, it's critical to perform to do performance monitoring based on live and previously unseen data, and to use these outputs for model retraining and performance logging. So there are a number of tips for each of those stages that I've described. Again, I hope that some of those we will continue during the discussion. So for data acquisition, we need to make sure that the data of high quality, and it's easy to say but hard to achieve. Then tool selection and integration. So it's really the software and hardware engineers. It's basically the key component here is to find the right choice of a model and correct architecture. And then during the debugging stage is to identify and fix the issue of, where pipeline doesn't perform very well. One final message that I would like to deliver is that there is a document that I found. It's NIST special publication 800, and I've shared this document in Google Google Drive that Ryan has created. And basically, this document, it's about 30 pages, and I encourage everyone to look at it. It basically lists a number of safe practices for secure software development for generative AI and dual use foundational models. So I'll stop here and maybe we'll continue into the discussion.